Good morning. Myself Dr. K. Manoharan, Associate Professor, Department of Biomedical Engineering. So today class we are going to discuss about 8251 interface. So 8251 is widely used for a serial communication. So whenever we need to communicate a one microprocessor with another microprocessor, or one microprocessor with microcontroller, or a microprocessor with PC, that is a personal computer, we need to use this 8251 interface. So 8251 widely used programmable communication interface chip. It is also known as UART, that is Universal Asynchronous Receiver Transmitter. So it commonly used in microprocessor-based system to enable the serial communications. So this 8251 facilitates serial data communication between a microprocessor-based system to the external devices like modems, terminals, printers, and all others. It supports asynchronous serial communication where data is transmitted one bit at a time without need for a separate clock signals. So bit by bit it will be transmitted continuously in a serial port. Look at the block diagram for this. So first one, this is the data bus buffer. So it will be integrating this internal data bus with this external microprocessors. So this is the read write control logic, reset signal, clock signal, that is code bar data, and read and write bar. So these signals will be connected to this read write control logics. So this is reset is for resetting the system, clock is for giving an clock pulses to this, and then C bar D bar, that is a control word or data word that will be selected by this C bar D bar, and then read signal, that is a read operation, write signal, this is the write operation. This is CS chip select. Remaining address lines will be connected to this chip select by enabling a suitable addresses. Look at this. This is the modem control signals, DSR, DTR, CTS, and RTS. So this will be a modem signals that will be used to provide an internet for the systems. That is CTS is clear to send, RTS is a request to send, and DSR and DTR, that is a data terminal ready and data set resets. Look at this. This is the actual blocks. So this side will be a transmitter side and this is the receiver side. Actually, it supports full duplex. Full duplex means dedicatedly we have a different channels for a transmitting and receiving. So simultaneously we can transmit the data and simultaneously we can receive the data at the time. Look at this. This is the actual transmit buffer. So whatever we are going to transmit the data, that data will be loaded to this transmit buffer. Here TXT, there is a transmit line, data line. So here the bit by bit data will be transmitted continuously. Look at this. This is the transmit control block. Look at this. TX ready. There is a transmitter ready. TX enable, transmitter enable, and TXE, there is a transmitter control. So these are the control signals that will be connected to this transmitter. So these two blocks will be a transmitter block. So based on these control signals, the data will be transmitted continuously through this TXD pin. Look at say this receiver side block. So this is the receive buffer. So whatever the data is received serially, so that will be stored in this receive buffer. Look at this. This is the RXT line. This data will be received and that will be stored here. So once if it receives all the 8 bits, the data will be copied to the data bus buffer. Look at this. That is a receive control signals. That is RXD. That is a receiver ready. Again RS receiver control and synchronous detect. So this will be used for a receiver. See, whenever you are interfacing one microprocessor another microprocessor, so this TXT pin will be connected to another system RXT pin, and another system TXT pin will be connected to this system RXT pin. So these two will be cross connected. So because whenever you are transmitting data from this side, that will be go for receiver side. There whatever the data is transmitting there, that will be comes for this receiver side. Look at this control mode instruction control word. So this D6, D7 that will be used for a framing control. So 0, it is 0, it is a not value, that is not used. 0 means 1 stop bit will be used. 10 means 1.5 stop bits, and 11 means 2 stop bits. So this decides how many data stop bits will be used with the data frames. Look at this D4, D5, so that will be given a parity controls, whether we are going to use it a parity or not, and then whether it is an odd parity or even parity, that will be decided by this D4 and D5. So don't care 0, that means 0, 0 and 1, 0. So these two cases it is a no parity. 0, 1 means it's an odd parity. 1, 1 means it's an even parity. Look at this D2, D3, this will be decides the character length. How many data bits we are going to transmit? Actual data bits. 0, 0 means a 5 bit, that is 5 bit data will be transmitted. So 0, 1 means 6 bit data, 1, 0 means 7 bits, and 1, 1 means 8 bits. So actual data bits with the parity bit and then start bit and stop bit have a complete frame structure. Look at this. This is the 0 D0 D1. This is baud rate factor. So baud rate factor means actually baud rate is bits per second. How much speed the data will be transmitted, that decides the baud rate, bits per second. So here this is the baud rate factor, that is whether the baud rate is increased or decreased, that will be decided by this factor. So 0 means it's in synchronous mode and 1 means it's in asynchronous mode with the into 1. That means actual baud rate will be used. 10 means asynchronous mode baud rate into 16 times. So actual baud rate into 16 is an transmitting speed of data. And then 1 mean actually asynchronous mode data baud rate into 64 times of actual baud rate. So this decides actual baud rate should be increased or decreased or depending upon the applications. Thank you.